So today I want to start with a little demonstration program that Professor Kasper has kindly provided me with to illustrate damped harmonic motion as opposed to a simple harmonic motion. So this is a computer program that simulates the physics, and right now you can see that we have dialed in a mass of 10 kilogram, a spring constant of 10 newtons per meter, and no damping at all. And so you see sort of the mass on the spring moving back and forth here, and it's completely undamped. This is a graph of the position as a function of time. So right now the motion is undamped. And therefore the amplitude as a function of time remains exactly the same. So this is a graph of the position. I can also turn on graphs of velocity and acceleration. And you actually can see that the phase of the velocity is different than that of the position, and the velocity phase is also different than that of the acceleration. And finally, we can also look at the phase of the position itself, as well as amplitude. So the distance is indicating the amplitude of the motion, and the angle with respect to the x-axis is the phase angle phi. It's a function of time. So let's stop this real quick and now add a little bit of damping to it. So now you can see that the amplitude as a function of time is reducing. And as it will turn out, the amplitude as a function of time behaves like an exponential. And eventually, the particle will come basically to a stop. And of course, velocity and acceleration decrease with it. So if we increase the damping further, then this will happen much more quickly. It will only take us 1 or 2 cycles for it to basically come to rest. And if we go still further, first of all, you can notice that this period in seconds actually starts to change as I'm increasing the damping to very strong damping. It becomes longer and longer. For example, now it would be almost not periodic anymore. There's actually still a little bit of periodicity in here, but you can basically already not see it anymore. And if I go to a friction coefficient of 20 kilograms per second, then there's not going to be any oscillations left. So the position graph just directly goes to 0 without ever swinging on the other side. And this condition is called critical damping. And it is important, for example, for car shock absorbers, because that's what you want when you hit a bump, that it doesn't take long to come to equilibrium. And if you damp the system further, which you can do, then it still doesn't oscillate, but it will take longer to reach, it will take longer to reach the equilibrium position. than before. This exponential curve is having a less slope, and therefore it takes longer. So we have basically 3 different behaviors. One is oscillatory with an amplitude that goes down as a function of time. One where there's no oscillation at all, and then sort of the limiting case between them. So let me now describe mathematically what you just saw. So we have the equation of motion as it's written in the book. So the acceleration is the damping term plus the oscillatory term divided by the mass. And this nasty equation can actually be transformed into a relatively simple quadratic equation if one assumes a general exponential behavior. So some value a times e to the zt. And then each of those derivatives, because of the behavior of the exponential function, just becomes a power of z. So we have z squared plus this times z. I'm sorry, this z shouldn't have been there. Plus k over m equals 0. And so one can transform that into a better form like that. And now we can see the 3 different cases. If this number here is negative, then the quadratic equation has solutions, and we are in the overdamping case. And that means that we can define some quantity that defines the square root of the negative of this one. And then we can have a multiplication of 2 exponentials, one using the damping term b over 2m, and one using this omega prime. The critical damping case is where this is 0, and in which case z equals just the damping term, and we get this behavior. However, if this part is bigger than 0, then this equation doesn't have any real solution. And from what I told you 2 days ago, there is a relation between exponential and trigonometric functions. And so what happens in that case, a trigonometric function appears instead of the exponential function. So we get still this damping term e to the minus gamma t, but instead of a second exponential like here, we get a cosine function plus some angle in principle. So, and this omega prime has the opposite, square has the opposite sign as this one, so that it's still positive. So if we graph this now, then here are the 3 different cases. Just like in the program before, we have the overdamped case, which takes a long time to reach equilibrium. We have the critically damped one, which reaches the equilibrium the fastest. And then we have the underdamped case, which oscillates around the equilibrium, but with an amplitude that is getting smaller and smaller. And if we draw the lines around it, then we recover the exponential function e to the minus gamma t. So damping is important. In some systems, you want to make it very small. For example, in a clock or watch, you want it to be as small as possible so that it doesn't warp the frequency, and also that it doesn't cost as much energy to keep the clock or watch going. At other times, however, damping is critical, and if you don't have any damping, then it becomes really dangerous. This is the case in a car shock absorber. The damping is provided by some viscous fluid, and if there's a leak and you lose that viscous fluid, I've once seen a car like that on the freeway, and it was basically bouncing from little bump to little bump on the freeway, and it makes it hard to actually control the car that way. So you don't want that, and what you ideally want is that the damping coefficient is tuned so that you achieve critical damping, and therefore when you hit a bump, the car comes to a steady state the fastest, and therefore it becomes the safest. Then, of course, another case where you like things to be damped is here in California is an earthquake. If your building has no damping at all, then it is far easier or far more likely to get destroyed in an earthquake, and if damping is built in. And in general, there are huge dampers built into buildings here to prevent that. So let me now calculate an example with damping, and just for ease I'm using a pendulum. So the example is as follows. We have a simple pendulum with a length of 1 meter, again to make things simple. It is set swinging with small amplitude oscillations, and after 5 minutes the amplitude is only half of what it was initially. So the question is, what is the value of gamma for that motion? And also, what is the value of the damping coefficient, which is proportional to the angular speed? So, and then the B part is by what factor differs the damped frequency f from the undamped frequency? And the answer is the equation of motion for the pendulum. We basically just have to substitute variables. So here we have the L, where we normally would have the mass, and where we had the spring constant, we get the G. And that helps us define what is gamma in this case. Gamma is B over 2L, just like it was before, B over 2M. So we see half the amplitude after 300 seconds. So that means that e to the minus gamma times 300 seconds must be 1/2. And if we take the logarithm of this equation, then we can solve for gamma. And it turns out this is the logarithm of 2 divided by 300 seconds. And we get a value for gamma of 0.0023 seconds. And that makes the B coefficient, since L is 1 meter, 0.0046 meters per second. So that is 1/2 of the answer of this problem, of this example. And the second half is how does the damped frequency f prime differ from the undamped? And for that, we use the relation between omega prime and k over m, or in this case, omega prime and g over L. So omega prime square is g over L plus the damping term b square over 4L square. And so we use the value of gamma, or b over 2L that we had before, and plug it into here, and we arrive at this value here for omega prime square. And for omega square, the undamped oscillation, that of course is just g over L, omega square. And so that's just 9.8 per second square, because L is 1 meter. And so once we have omega square and omega prime square, we can take the square root and form the ratio. And we find out that this ratio differs from 1 by 2.7 times 10 to the minus 7. So that is a very small frequency shift. And that the reason for the smallness of the frequency shift is that this is a pendulum is a very good oscillator. So damping tends to be small. So the next thing we would like to consider is what happens if I have damped oscillations and I apply a periodic force to it. And it gets increasingly more difficult. So in this case, I will spare you the math and just give you the answer. So we assume a periodic driving force with frequency f or angular frequency omega. And we can define a natural frequency of or the resonance frequency. And we do that as before. I'm sorry, I forgot the square here around the omega 0 square. So this is simply the spring constant over the mass, or the constant of gravity over the length. And if f is approximately equal to f0, meaning that the frequency of the driving force is roughly equal to that, then that of course also means that omega equals omega 0, since both are just multiplied by 2 pi. Then resonance occurs, and small forces can produce large amplitude oscillations. And I will try to demonstrate that here. This is actually a resonator. So even without the microphone, I can make a fairly loud sound with the help of this resonator. In this case, naturally grown resonators. And basically, such resonances are the basis for most instruments, most music instruments have resonances occurring in them. And if one is really an expert, which I'm not, then you actually can control the pitch, because this resonator has multiple frequencies, not just one. So other examples of resonances, as I mentioned before, a freeway system can behave as a resonance system. So this is, I think, a Los Angeles freeway after the 1987 earthquake, one of the big earthquakes. I wasn't here yet. So now after the fun, we'll have to do just a little bit of math. So we have the equation of motion, where we now added another term, this obnoxious external force, which led to the bridge collapse, for example. And we find that the resulting periodic motion is with the frequency of the driver, not of the frequency of the system, not the k over m, but the square root of k over m, but the driving frequency. And in case of perfect resonance, it is actually shifted by 90 degrees. For other cases, it's shifted by some angle phi 0. And one can calculate the amplitude of the oscillation by this expression, and the tangent of the phi, the phase shift, by this expression. And what I want to point out is only qualitatively here that if you have a heavily damped system, then the amplitude is smaller than if you have a lightly damped system. And of course, it becomes infinite if there's no damping at all. And also, this resonance curve, as it's called, will be narrower if it's lightly damped than if it's heavily damped. And one can actually assign a quality factor to the system, which has no units, and is given by the damping and the natural frequency, and in this case the mass. And then one can completely characterize these resonance curves and associate them with different quality factors. And by the way, this curve C, which doesn't have a peak at all at omega 0, that is the overdamped case. And B is just heavily damped, and A curve is lightly damped. Yeah, m is mass in this case. So we are back to the spring. So you have the spring constant k and the mass m. So let me now summarize the chapter. So we have learned about simple harmonic motion, which is characterized that the force is proportional to a displacement from an equilibrium position, like this. The motion is sinusoidal. It has a period t, which is from trough to trough or from crest to crest. Then, so that's the time to undergo one cycle of oscillations. then the frequency is the inverse of that, and it's how many cycles you have per second. The amplitude is the maximum displacement that you observe. The angle phi is sort of the offset from a given crest to the origin, to time equals 0. And the omega, or the angular frequency, is 2 pi times the frequency, and omega square is given by the ratio of the spring constant divided by the mass. And the amplitude and phase, they depend on the initial conditions, meaning what happens at time equals 0, what displacement and what velocity you have.
Is phi and wavelength the same thing? Because isn't the wavelength that same definition?
You mean the time period. It looks like this because I have unfortunately chosen an exact cosine function. But if this one was actually shifted a little bit, then the end of the arrow here wouldn't be at the crest. So in general, let me draw another picture where this is not the case. I just had this picture handy. So in this case, the period is still given by this, or for example by that, but the phi, it continues like this. The phi only goes to the origin, not to the next crest. So second part, the total energy of the simple harmonic motion is a constant, and it is comprised out of the kinetic term and the potential energy term. And so the energy is constant, the total energy is constant, but it changes back and forth between the kinetic and potential energy. In the case of the simple pendulum, we can just replace k with the acceleration of gravity and m with the length of the pendulum, and we get the exact same formulas. And therefore, since omega only depends on gravity and the length, which is easily measurable, one can use it to measure the acceleration of gravity. If there's any kind of friction, then this leads to damped harmonic motion. And in this case, there are three categories. Oscillation occurs if the system is underdamped, and then you have a time-dependent amplitude which decreases exponentially. Then there is no oscillations occur at all for critical damping or overdamping. In both cases, it's sort of exponential decay of the displacement, but the time to reach equilibrium is different. And lastly, if an external force is applied, then the amplitude can get very large if the frequency of the force is very close to the natural or the resonant frequency of the system. And that is called resonance. And a longer damping leads to a broader resonance curve. A larger damping leads to a broader resonance curve than a smaller one. So I'm going to conclude with a little outview about the next chapter, which is about waves. Waves are related to oscillations. They have something to do with oscillations, but they add another element. So you might want to move. I'll move back here so to... okay. So if I have a taut wire like this, then wave propagation on that wire is possible. Let me wait until it's quieting down a little bit. And you can see a pulse traveling back and forth and getting reflected at the ends. And as it turns out, if you change the tension in the wire, let it hang loose a little bit, then it takes longer for the pulse to move back and forth than if the wire is tight. Of course, if I tighten the wire too much, it's going to tear loose from that post, so I'm not going to do that. So, and I have another little program to make this easier to follow for people who are sitting in the back. So the interesting thing about the wave is that the shape sort of seems to be traveling this way, but the actual rope, of course, doesn't travel. Otherwise, it would uncoil. And so a particle on the rope, it just oscillates up and down. And in fact, you see this for one particular value of x, which is given by the cursor here. It changes between up and down, and goes up and down. And I can try and follow this crest of the wave with the mouse, and you see that the displacement remains approximately constant, but at a different position each time. While when I move to any position on this graph, then each part of the rope only moves up and down. So there are two kinds of motions. One is the motion of this shape, which seems to be traveling this way. And then perpendicular to that, there is this up and down motion. And that is why we call this a transverse wave. And it's exactly the same kind of wave that I excited here with the hammer. So thank you for your attention.